In this video, we're going to talk about how we can determine whether or not a molecule is polar, and we're going to use electronegativity and the structural arrangement of the molecule to determine that. So, electronegativity, again, is the strength an atom has when attracting electrons in a bond. And if we look at, we're going to look at molecules of each of the 5 geometries that we talked about. The first one we're going to look at is tetrahedral. So, in this tetrahedral molecule, CF4, you have a carbon in the middle, which has an electronegativity of 2.5, and each of the atoms attached to it is going to be a fluorine with an electronegativity of 4.0. So fluorine is much more aggressive in attracting electrons in a bond, and it's going to be withdrawing electron density from the carbon. And that's why you see that all of the fluorines have a partial negative charge, and the carbon has a partial positive charge. So there are bond dipoles that exist, and those are shown in red. However, there's no lopsidedness to the molecule, and it's very symmetrical in its electron distribution. Therefore, we would say that it's nonpolar. If we look at the other tetrahedral molecule, you have carbon with 2 fluorines as well as 2 hydrogens. Since carbon's stronger or more electronegative than the hydrogens, it's going to withdraw electron density towards it, leaving the hydrogens partially positive. And then the fluorines, again, being the most electronegative element, are going to further withdraw electrons in that direction. So you have partial negative charges on your fluorine, partial positive charges on your hydrogen, and a very big, very tiny positive charge on the carbon, which you wouldn't even have to draw. But you can definitely see that there's a lopsidedness to the electron distribution here. The fluorine end of the molecule is going to carry a partial negative charge, and the hydrogen end is going to be partially positive. So we drew out the bond dipoles in red, showing the difference in electronegativities and the directionality of the electron flow with the bonds. And with the green, we drew the molecular dipole. So you can see that one end of the molecule is definitely partially negative. So that would be polar. Looking at the next shape, trigonal planar, you have BF3, again, symmetrical. The electrons are being withdrawn to the perimeter, but they're being done so in a symmetrical fashion. There's no lopsidedness to it, and we would call that nonpolar. If we look at formaldehyde down here, CH2O, the carbon is withdrawing electrons from both hydrogens, so those become partially positive, but then the oxygen withdraws the electron density because it has an electronegativity of 3.5. So, this molecule, the electrons are definitely being pulled in one direction. And then, lastly, with the linear shapes, where you have no unshared pairs in the central atom, or if it's only just 2 atoms, right? The first one, there's not even bond dipoles because the 2 oxygen atoms have the same electronegativities. There's not going to be bond dipoles or molecular dipoles. That is very much a nonpolar molecule. Carbon dioxide, there's a difference in strength between the carbons and the oxygen, but the electron density is being pulled equally in opposite directions. You do have the partial charges, but overall, there's no positive or negative ends to the molecule, and we would call that nonpolar. However, these linear molecules are polar because they possess asymmetry. In hydrochloric acid, you have H being weaker than the chlorine. Electrons flow towards the chlorine, partial negative end, partial positive end. Then HCN, same deal. The electrons are flowing in one direction. You have a buildup of electron density towards the nitrogen end and a lack of electron density around the hydrogen, making that end partially polar. These 3 molecular geometries have no unshared pairs on the central atom. And when you have that as the case, if the molecule is symmetrical, it's going to be nonpolar. And if you have asymmetry, you are going to have a polar molecule. And we'll talk about the implications of that on Monday. Now, the trigonal pyramidal shape and the bent shape both have unshared pairs in the central atom. So by default, they have a built-in asymmetry to them, and they're gonna be polar. Now, if we look at ammonia, NH3, you can see that nitrogen is pulling electrons from the hydrogens, and you're gonna have a buildup of electron density around the nitrogen, making it partially negative. The hydrogen end of the molecule is gonna carry a partial positive charge. Water, similarly, oxygen is gonna be pulling electrons away from the hydrogen.